Welcome everybody, you're watching Mr. Fugu Data Science. Today we're doing the basics of maximum likelihood estimation. Now, let's think about this. Suppose that we have some data. We suspect it has a given distribution type, but we don't know the parameters. Well, what do? Well, this is where MLE shines. So the parameters are found where they actually maximize the likelihood of generating our model from our given data. We're trying to figure out basically what model will best describe these data. And having a little bit of knowledge prior or domain knowledge will really help in these circumstances. I would like to say, before we move further, thank you to the recent subscribers and viewers lately. I greatly appreciate it. Now, as you increase your size of your data, if it's really large, like the sample size of your data, the variance will actually become the unbiased variance estimator. And also, you can generate a normal distribution and normal confidence intervals as well. So let's get into a little bit of this. Basically, each probability distribution will have unique parameters, and as those parameters change, a different probability distribution is generated. The parameters for each model will fall into a family of distributions based on the parameters you have. For example, a normal distribution has the parameters of a mean and a standard deviation, right? But as those parameters change, it creates a new model. Therefore, the family of distributions is generated by varying your parameters. Let's look at some plots and see what's going on with these particular parameters for the normal distribution. As we have the mean constant and vary the standard deviation, you'll see that as you increase the standard deviation, the plot will broaden out or flatten out. Now, if we vary the mean and keep constant the standard deviation, you'll have a shift left if the mean is going to a smaller value and to the right with a larger value. Now, in the real world, you'll be given some data that's observed, and you need to find some kind of model that best describes this, all right? And you're not always in a position to transform your data, log, reciprocal, square root, or whatever the transformation may be. So if you would like to use the maximum likelihood estimation, remember that if you have a distribution in mind and you're looking for the parameters for your data, that's the gist of why you're going to use this. The other thing that needs to be mentioned, well, why can't I, in this circumstance, just generate the mean and the standard deviation from the data? Well, that will not necessarily give you the best approximation or estimate for the population. That'll give you what you have for your current sample. Now, let's think about this. We're looking at this as the likelihood of some values x, which is your observed data, and your parameters, all right? Where the L will stand for the likelihood, and it's just some true parameters of theta given your observed data. The right side is a function of the data given a particular set of parameters. It's the reverse. The semicolon is a distinction and not the same as if you used a bar for conditional probability, where you would say, if I had a bar right here instead of the semicolon, you'd say, given some parameters theta, what is my x? And you do your probabilities based on that, right? Multiplying them across. But the distinction is, I'm letting you know that we have our parameters here, all right? Now, let's do some math for that MLE, since that's what you came for. At least I hope you did. But you have some nasty truth. The first thing, you do not necessarily have to have a unique value for the MLE, and you also don't even need one to exist. But why? That's because of concavity. Think about this in terms of if you had a function that was multimodal, like it just had a bunch of peaks and troughs. That's a situation where you would have issues with concavity. Okay, this comes up a lot in machine learning, for instance, and it's a big topic and a big deal. And there's ways to deal with this. If you have situations such as this, approximation methods would be best suited for you. Now, we're going to get into some super fun times, but not just any kind, super fun, happy times with our little panda friend. So we're going to start with our likelihood, and we're going to pull this right side, and we need to look for the instance of each x, all right? So each sample piece of data, x1, x2, all the way to xn, right? And we're going to multiply all these together for conditional probability, all right? But now we got to do a little bit of trickery. And the great thing is we're going to convert all of these multiplications into additions and use the log. And we're using the log for a few reasons. One, it's not going to change or affect our distribution. The second thing is anytime you have the opportunity to change a multiplication into an addition, you're in good business when it's computing power, as a side note. So we're going to run those multiplications for each value of x. We're going to find our given theta. We're going to take the log of this and separate everything, all right? And then we have to worry about using some derivatives. And the reason we're going to use the derivatives is because we're trying to find one with the first derivative where our peak will have that horizontal line equal to 0. And then we're saying, bazinga, we're there. We're getting our little point. We're able to find the best parameter that we're looking for currently. But then you need to use that second derivative test because you need to see if you got a negative slope going there. And that's something you need because you got to remember concavity, right? So this looks oversimplified and we're going to get into this a little bit, but you're going to notice something. If you have that suspected distribution, you would like to replace it, you would put it right in here, okay? Now, I need to mention something. Some really good approximation methods if you're in a position where you either have highly parameterized data or it's non-convex. Here's a few methods that you can look at, which are really useful and will come up quite often if you're doing any kind of machine learning or any kind of non-parametric type of regression or something like that, you know? So let's assume that I made up some data, some fake perceived IQ data for people who voted for a particular president with a weird tan and goofy looking hair. And let's just assume that they have some really terrible IQs. Okay, this guy over here, he's probably the best one, or her, who knows. But then you got some really low balls. You say, oh no, what's wrong with these people? They don't seem very bright. And you plot this out and you do two transformations. You look at the original data to get an idea of what it looks like. You do a log transform to see if that might clean it up. And you do a square root and you say, oh, the square root's not looking too bad. It's got a long tail though on the left side. Same with this one here, but it's a little deceiving. So let's get a little clearer picture. So we plot this again. We say, okay, this distribution is looking interesting. I still notice I got this tail on the original data. My confidence intervals here look kind of terrible. I do that square root and that's looking, almost the same, except I got this hump that's kind of notched in here, right? You say, well, how should I deal with this? My data does look like it has a trend, which would be normal, but how can we maximize our parameter for our given standard deviation and the mean shifting? So let's figure out what we can do with this. Sometimes you may have a distribution that you feel may likely work with the data you have, and then later on you may reconsider and figure out, well, I might have been wrong when you replot. Let's get into this math once again. So we're taking our parameters with our given data, we're throwing in the exponential function, and then for each value of x, we're going to run it through our exponential function. And we need to find the best value of our standard deviation and our mean. And since you're doing this for each individual x, we're also going to multiply this through and expand this out from x1 to xn. Take the log of it like we mentioned before here. Since we're going to use the log, all these multiplications get that trusty old addition. We need to simplify our data. So if I'm only showing the first instance of what's going on, you're going to now take this, and since you have these two, which this and this were multiplication, you're able to expand that into an addition now. We're able to take this from this denominator and bring it out. And now we're going to expand this once again and separate these, okay? And we need to repeat the process for x2 to x of n, okay? And that's what you'll end up with going on here. Because you have n occurrences for all your x values, that's why these n values are here, okay? And we're basically summing up each one of these for each individual value of x as well. But now we need to take that derivative. The first we'll do is with respect to the mean. This is what we're going to use for taking the derivative. The first two portions here do not have the mu or the mean. That's why these are canceled out to 0, and you're only left with this. Okay? We got to do a little work with the chain rule where we're bringing this superscript here down. It'll cancel out in here, and then we would have a -1 that would come from this mu, which changes the sign that you noticed here. Alright? And this is what you're left with. Now, to expand through this, we have n occurrences of mu, and we still have our sum. And if you notice this, the only thing you get back is your sample mean. Alright? So you're basically adding all of the values of your x and dividing by the number of values. Okay, fine. We get our sample mean. Now, the same thing that we do for the standard deviation, we start with this. We're finding anything that has our trusty old friend, the variance. But what happened here? So, since you have the log becomes 1 over, so you have n over this. Since this is in the denominator, it becomes a 3, and you have to take out the sign. So to be, you're in the denominator, so it'd be a -2 that comes out. This becomes a -3. So that you end up getting that plus. And then this, just treating it as a constant. You got to do some manipulation. You got to bring this, there you are. You got to bring this over. Then you multiply by this. Cancels out, you only have 1 left. Get rid of the squared value. That's where you get the square root from. And if you notice, I put something as a distinction. This is the biased estimator. Alright? The unbiased estimator would have been n-1. So keep that in mind and try not to get confused, alright? If you want to see a proof, it's in this right here. So go on my GitHub and pull this code. I left a PDF as well as the Jupyter notebook. I decided to look at the CDF to see how this looks towards a normal distribution. So it's looking okay. That's fine. Tails are kind of long though. And I say, can we directly compute the mean and the standard deviation from the data? But this doesn't really mean, like I said before, that we're representing the population of the data. That's only with respect to the sample, hence the use of the MLE. So, what did I do here? I decided to plot in red the original data. And this vertical line here is the mean of the original data and the shifted new values of our fitted MLE. Okay? This plot right here though is kind of an issue because I initially used a random variable to generate our new fitted. These values here are your MLE values for your mean and your standard deviation. I just didn't shorten up the significant figures. So I decided let's plot this again but standardize our data and not have a random distribution created for our new fitted data. So now I created this new data where the original data is our green with our green line with the long tails, and this red one is now our fitted data with the original mean in the blue vertical line so we can see the shifting. So this is what it would look like with the new fitted MLE model. And if you notice, these tails look extremely short and they're stopping at the edge of each one of these data. I said, okay, fine. Let's see how this looks under the new CDF. And I plotted that and you see that it does look like a normal distribution. The hump right here and this little tail towards 1 are only a reflection of what our data look like with respect to the new mean and standard deviation, which is basically giving us the best model for what we're given currently. Some last thoughts. You can't always assume your data will fit an exact model. Approximation methods are usually a good call on real data, and don't blindly believe everything you hear or everything you see. Alright? Please like, share, and subscribe, and if you subscribe, turn on that notification bell. I greatly appreciate it. Thank you for watching. I'll see you in the next video. Bye.